So I'm going to be talking about what we've been doing at Machine Zone and sharing some of the stuff that allows us to basically run this game. Basically what we do is that we have this, we build a highly engaging multiplayer game. So it's all about everything is online, always connected, and making sure that people can engage in social activity as well as gameplay activities, which is basically fighting, because our game is about fighting or engaging in some sort of battles. So I would like to talk about scalability first, because this is actually one of our major point when it comes to dealing with the mobile game, because we are not on the web per se. We're actually pure mobile, and we've been doing mobile for 5 years, which means that we kind of understand the play when it comes to launching a game that will grow and double every week potentially, and what that means in terms of ensuring the activity and the gameplay will be up to the level the players are actually expecting it. So massive scalability is actually something that is actually very important, because it is obviously tied with Erlang, self real-time ecosystem. And I will talk about what we consider it to be the upper bound, and how do you position yourself into an environment where you can actually keep on scaling up and scaling out. So I will explain how we did reach some kind of scalability nirvana, which I know it sounds pretty crazy because people think it's kind of not possible, but actually it does. I mean, if you look at WhatsApp, they've been doing some pretty incredible stuff. So I will start with, I don't know if everybody is familiar with Brewer-Cap theorem, which is basically, Eric Brewer came up with this in 2000, and he claimed that out of these 3 different properties, which is consistency, availability, and partition tolerance, you wouldn't be able to achieve the 3 of them at the same time. You'd have to sacrifice one. And it's been pretty true. It's been a huge debate because people claim that they could fix it. You have a lot of data storage these days that, actually as kind of claiming that they're actually fixing it. But when it comes to really pure, handling of all these 3 properties, it's actually very hard, depending if you handle the network latency, and what does that mean when we lose one of your node or some part of the network. So consistency is something that you must be familiar with database systems, right? Because database systems, I mean, that's my world, is really what does that mean to make sure your data are consistent across your cluster. So in terms of you want to make sure if one of the nodes goes down, your data is still going to be consistent with the other nodes. And that ties into the second area, which is availability, which means what happens when one node goes down. So basically, does your system stop? Are you actually reading data that are inconsistent in your cluster? How do you keep your application running? And partition tolerance is a very, very important topic, because in a distributed environment, you can expect, and you should expect, to have some network outage, even internally, not necessarily on the web, but more on your cloud or in your with your hosting provider. So all of these, the consistency part is kind of something that database systems have been working for a long time in order to solve and address. But the partition tolerance, as far as cluster goes, is something that the new data storages are facing, because you want to keep increasing nodes in your cluster, but at the same time, as you're adding more nodes, you're introducing more risk to network outages, potentially. So you have to account for that. And what does that mean? That you have to understand that what happens when something goes bad. This is really again, it's something I want to stress, because a lot of the time, people are actually coming up with environment that are supposed to work very well, but when it comes to losing one node or something makes your system behave in a non-efficient way, then you start having some very I would say unwanted behaviors, and that could lead to angry customers. So for us, it's everything at Machine Zone, we treat everything as the system cannot stop. Basically, it's 24/7. So we want to make sure we can always run and non-stop, because if you stop, you basically don't make any more money. You have hungry people. They leave the game and they go and try other games, because you have a lot of games on mobile. So it's actually, this is something that we want to make sure doesn't happen. So I would say treat everything as a single point of failure. This is true. I mean, this is really something that you might want to. I do it because this is something that is when you're dealing with large-scale systems, you don't necessarily see single point of failure right away. But as you grow the system, you may actually start trying and basically understand okay, it seems like this could be a potential candidate for a single point of failure at some point. So this is something that you need to assess, which is basically means locking. Locking is a good example. Logical locks by definitions are very slow. It's just a fact is that so you have hardware locks, which helps, or you just don't do, or you do like mutex, and semaphores, and basically to give you an example, I mean a logical lock versus a spin lock is actually which is a hardware lock can be the difference is actually tremendous. So when you're dealing with locks on a system, if you are doing too much, if your concurrency means that you're going to be sharing some of these resources, a lock could actually bring your system down, once you have a very large number of users, playing. So this is something that we assess and profile. So bench earlys and always, that's definitely the big thing that we've been doing at Machine Zone. It's actually bench always. Bench is not benching is an option. Invest even if it means spending 2 months building a bench system, you just have to do it. The thing you want to avoid is as your product grows, you have to refactor. I see too many companies doing it. They actually grow and they end up refactoring all the time, and this is something that is annoying because you are basically everybody's stressed, and then you're affecting your customers with that. So no compromises are fine. I'll explain why in a minute. No one size fits all is true. So don't try. I mean, my recommendation is not to try and use the same data storage for everything. You really have to assess what you need, what type of consistency, and also what type of performance. Some systems you may need to have eventual consistency. Some of the systems you may have to need strict consistency. So when people talk about SQL versus NoSQL, it's a false debate. It's SQL is kind of important for some of your processing. NoSQL is important as well because you may not need the overhead of SQL when you need certain type of processing. But SQL is definitely something that you just cannot throw away because the expressive power of SQL combined with the actual performance of the data store is something that will give you some interesting capabilities when it comes to implementing your logic. So the challenges we face we've been facing is this one. So a worldwide reach. I mean, we are basically on iOS at the moment. We are going Android actually next month, which means we are pretty much everywhere on iOS, and that means that you have to basically account for network latency. You've got to account for different time zones. We have one single world. We don't do instancing. Just because we don't want to do instancing ever. What we implement is a single world, meaning that we will have all the players at some times in the same world, and that's what we want to do. So that's why we need to have something that can scale, because we just cannot say, okay, let's have another server and let's put these 300,000 users in that particular instance and keep doing it. I mean, most companies out there on freemium play tends to do that because that's the easy route. But as far as keeping the world engaged and a true real world, single world, this is a much more challenging implementation, but that's also rewarding and engaging because it keeps your world always active, basically. So no language barrier. We made that also an interesting aspect, what do you do when you have people from all over the world in the same chat room? And being able to deal with a growing game again, 40 million daily active users, from 5 million to 40 million, 100 to 500K concurrent and active users. So that is something, and these games cannot stop. So that's one example. So, sorry. That's an example of the game. So on the left side, you've seen it's like the world map with different provinces. You can see them as states. And on the middle, you've got a massive attack of 100 people attacking one kingdom, basically one empire. And so you can see all these armies on the map are basically all real time. So all you see that is a real time map of active players actually working together. So the challenge we faced, and that's why we're using Erlang, is that we had to basically make sure all the battles were synchronized. and what will happen at the same time. Because when you have 300 people, in a same alliance, or 100 versus 100 people attacking, similar cities or other cities, or you need to make sure like they actually synchronize well, and the latency is taken into account. Because if it doesn't, then they will get pissed and they will start saying like, I was supposed to win this fight, I was late, and then they quit the game. So we have to do a great deal as far as synchronizing and making sure like the latency is addressed, as well as real time is actually working on the map. So I'll show an example in a minute, but this is the wars we are facing. It's like, this is really like people like engaging in this massive war, massive activity, and the map is actually real time on your phone. I mean, that's really what you see. What you see is what you get. So I'll show, yes, I'm supposed to, sorry. I'll show an example of, after that. But basically, what we have to do is real-time chat. So real-time chat is something that most people have in the app, and I know all of you have been using Ijabirdy. I'll talk about it in a second. Real-time events, because we need to, everything in a game, is an event. And we do, massive parallel broadcasting of, again, of real-time messages, auto-subscription of, events, basically, that you want to be subscribed. Real-time push notifications, and always being, HA is also very important. So how do you achieve 4 nines? It's actually very hard. I mean, 50 minutes done per year, it's hard. I mean, for us, it's hard because it's not the software most of the time, it's the hardware. I mean, we are facing issues with the hardware and network, so we're working on that, but it's actually pretty hard to keep it like under an hour a year, obviously. So scaling, I talk about that. I mean, scaling up and scaling out. We decided to scale up and scale out, meaning that we have very, very fast machines, a lot of RAM, very fast drives, a lot of CPUs, and we have, this is where we can handle a lot of users per, per instant, per node, basically. And memory is free, so for most of the time, it's when I say free, that it's actually close to be free when you look at the money you spend overall on the whole, hardware. Distribution is important. Redundancy is important. Failover, auto failover. Everything should be auto failover. If you don't auto failover, you are basically having to deal with either a performance problems because you're missing some node in your system, or you're going to be dealing with not being able to keep the game running. So that's, and cluster is a must. Social, no language barrier, so I will talk about it. It's something that we're also using. We've decided to bet and basically make, how do we solve the language, the languages of the world, and that's something we invested like about 2 years ago in terms of like, how do we distribute real-time chat messages and at the same time translating them. So we've hired a team and we built a team to basically build and implement real-time machine translation, which is basically something that allows us to process in real-time chat speak type of text and distribute and process, basically translate up to 32 languages in a single chat room, under let's say 1 millisecond. I mean, we deal with microseconds. We try and really keep things as fast as possible in parallel. So, and that's one of the challenges we decided to make is like translate everything by default. Don't go and let people ask every time they want to check if a chat is in French or, and it should be French. No, we do it like automatically. We translate based on your language settings. And that is something that a lot of the social apps these days don't even provide. If you think at Facebook, and Facebook is as kind of a, it's kind of a mode where you have to actually ask for a translation, and Twitter is starting to have it, but it's still, so we do that by default, and people have been liking it because the system is smart enough to learn and get feedback from the players and increase the training of the engine. So that alone is a pretty interesting feature because it combines like some Erlang and C++ to basically process this real-time chat during, even during large spike, we have to do that. So everything is distributed and to do that. So I will try and show a video. Hopefully it's going to work. We'll see. Okay. Cool. So this is like, if you see here, This is like a single word, like multiple devices. And I'll show the map as it runs. Sorry, it's hard for me to draw it from here, but basically, okay. So this is all of this stuff on the map are actually operating in real time. So you see here, these guys are actually crossing, and you'll see the army on the left is going to cross the device. This is it's using different type of phones, and it's crossing it. So it's totally. So this works on it's yeah. And then this demo is another demo we've done in order to actually show what event Erlang is bringing to the social gaming space when it comes to massive multiplayer play. So you have like a bunch of iPads in that case, and you start here, and you can see the horse crossing the iPad on every device. So it's done in real time. So this is the kind of stuff that we do all across our app. The UI is real time as well. So and that's something that people translation. Well, it's also of course translated. Everything is in parallel. So we do a bunch of like kind of like real time. Sorry for saying it so much, but that's actually true. We actually try and cause everything to be real time in the game. So which means like we do a lot of push. We don't do pull for most, except if it doesn't, your gameplay doesn't require. Otherwise, we just sorry. I need to go back to my. Okay, so I was at this. Well, what's the secret sauce? I mean, obviously, I talk about it. It's like understand what you're building. It means like where you are going. On mobile, you may be dealing with like you start a game, you deal with like 10K concurrent users, 20K concurrent users, and then the next day your game is successful. You deal with 50K, 100K concurrent users, and then you're dealing with like 200K, 400K, and it becomes like you have to basically keep that load, and you have to make sure you can actually sustain that, especially spikes. What does that mean when you have like 50K players coming up under a second, or 2 seconds? If there is a mass like push, and they're all trying to get into the play. So this is being skeptical is good. I'm French, so it's very natural for me to be skeptical. But I would say, don't trust. Personally, I don't trust software. I just bench it like crazy, and then I profile. And I do negative testing, a lot of negative testing, and then if it fits the bill, I will just put it in production, and that's why I personally I tend to use like software that I know have been pretty robust, solid, and that's something that unfortunately I know that people are not doing enough. So I would say open source is a good thing, and it's a great thing, obviously. So fork as needed. Take open source and fork it and contribute back. So we intend to contribute some of our stuff, at some point when we are ready, because we have to support it. You have to be ready to also basically support your own contributions and rewrite only as necessary. And so we, so profiling everything. We profile like we have like C++, C, PHP. We profile PHP all the time. We analyze any contention point. Erlang, the same, eprof, fprof, we profile. So you have to, because again, this is if you don't do it early and try and guess the single point of failures or bottlenecks, it will hit you when you don't want to, because at that point it will be like a lot of stress. So no single point of failure is the ultimate goal, and it's hard, but it is something that you have to really put your mind into, because this is something I learned in database systems as an engineer. Every lock, every instruction, it matters. So at this point, you have to really, apply it to anything else, because it becomes like everything becomes like a contention. And you see it from these apps like WhatsApp. They have all these great like improvements, because they are finding bottlenecks that most people don't. But when it comes to mobile, you will hit these bottlenecks as soon as you start having a game which needs to have like more than, I would say 50K or 100K CCUs, concurrent users. That's going to be coming. So Erlang, okay, I just explained why we picked Erlang. We picked Erlang like about 3 or 4 years ago, and it was like something that I found That was actually very interesting and refreshing for me because it's not just a language, it's a platform. And having a platform is great because you get certain capabilities that other platforms don't offer. You know, it's like if I mention Java, for example, the distributed aspect of Java, of Erlang, and all the properties that gives you is something that we've made it like a must at this point in the company. So all of our foundations are pretty much written using Erlang. You know, we have systems running for 2 years. We don't need to reboot anything. We just hot swap the code. Scales greatly. Thanks to Erlang Factory and all these great guys to also like help us like identifying some issues with, for instance, like amnesia and stuff like that. That you know you have to be very careful about how you use it. But overall, I mean, this has been a great experience for us, and we want to, you know, we will and hopefully contribute as much as we can to promote Erlang. Functional programming has been an issue in a company. We do have. So we have a solution to kind of promote Erlang without necessarily forcing engineers to use Erlang, but it's actually hard because most of the, for instance, gaming engineers would want to do something else than Erlang. They would like to use, you know, something simpler as a language to implement our logic. So, but some of them are okay with it. Some of them prefer to do something else. So it's hard to get everybody to be on the Erlang bandwagon, but you know, you try to come up with a compromise. So this is what we've done. Real-time chat, real-time chat speak, transformation and translation, real-time events, timers, push notifications, and we built our own message queuing system because we used some other famous message queuing system out there, but we found some scalability, so we had to basically, you know, decide to build our own. We kind of forked Jeopardy for us to put a lot of improvement. Yeah, no XMPP presence. We rewrote pretty much the group chat XMPP to be a lot more distributed. It means that you could actually support very large chat room across nodes. And that is something we wanted to have because we had some chat rooms that people would be actually, it would reach like, you know, 50K or 70K players in there. And of course, we found a way to make them not talk at the same time, but basically, because you have to. But this is something that we had to do. So what's interesting here is basically the full chat persistence and history support, real-time chat translation. XMPP, we found it pretty heavy, so the way to go is really to have your own protocol if you don't need to expose XMPP, you know, outside, because it's just heavy as XML-based, and you know, and the size, the footprint is also the cause of Jeopardy being sometimes a memory hog. Chat translation, so this is like C++ on Erlang. We do a lot of processing using Erlang as far as orchestrating the chat transformation. We support 32 languages. Right now, I mean, we can process like 1,000 translations a second. And this is based on a scale-out architecture, so we can actually scale it out by just adding nodes to the system. Real-time events is definitely the big thing. It's publish subscribe model. It's like used everywhere in the game, and this is something we built on our own. It's kind of a clusters of clusters, small groups of nodes in a cluster that we use in the Erlang ecosystem. Timers are like, we have timers to handle because in the game, you know, obviously, you know, how do you deal with timers when you have like a lot of players, you know, cooperating to attack someone. Again, you could have like, so you need to be able to synchronize. We built a system which is highly resilient. If we lose the backend, it will keep running. If you lose the node, it will keep running. This is basically, again, this cannot stop. It's like you have to have a system that will always run. So it took us some time to build it, but it's been running so far like for almost a year, very good. And we do like 2 billion events per day, pretty much. It's growing. It will pretty double in a couple of months because we are launching a new platform. And yeah, 40,000 a second. That's you know, kind of nice for the games. These are actually game events. Yeah, so that's kind of the game layer, and PHP, Lua, Python, and you have like the real-time event system with a bunch of subscriptions and timers, and then you basically, we can mass push, you know, like a lot of messages to the phone when they are offline, users are offline, or when they are online. So we have like 2 different channels. And at this point, all of the Erlang nodes are communicating and understand like requests as they need to basically ready to process for the player. The message queuing system is something we built because we wanted to be able to have a system that would allow us to process messages, and using specialized consumers, written in Lua, and Python is another thing that we're going to do next. But Lua is definitely something that I would like to talk about because Lua with Erlang, is a good combo. So we used it for message queuing system. So we have the Lua JIT running inside Erlang, and we can have consumers basically executing Lua logic. So this is something that we've been running in production like for quite some time. It's running perfectly well. So you can actually target, you can store data in different data store like AMQP, standard protocol, RDBMS, and also log files. 30,000 messages per second per consumer on a fairly, it's not necessarily a fast box, but 2.2 gigahertz. It's an older MacBook Pro, I'd say. So, and it's linearly scalable. So that was a goal, to be able to linear scale as you add more nodes. Game logic layer, PHP, Lua, Python, Erlang, C++, for Core Services Foundation. It's a great combo. It's basically, Erlang plus Lua for us is great because it gives us a mean for engineers to not complain about Erlang, game engineers. At the same time, they get interested because they understand what it means to run inside, an Erlang, environment. So Lua JIT is extremely fast. So we can basically, there is some interesting challenges when it comes to calling Lua inside Erlang, but overall, it's been working out pretty well for us for some of the processing that we have in the game. And that is something that we will definitely talk more about it as we become more public about what we do, because this has been really rewarding so far for us. This is another thing that if people are using, like if you have PHP legacy applications, you can add real time to PHP. I know it sounds kind of crazy to say that, but there are a lot of PHP apps out there, and I think it's nice to have Erlang being kind of like bridged into PHP. MyPeb is like a kind of like a, well, that's what is open source right now, which is the PHP Erlang bridge, and we kind of like did a complete rewrite pretty much, and we'll contribute back. That's the goal. So we've added like load balancing of nodes in PHP, node failover, persistent connections, being able to reestablish connections. And that's really was very, very good for us because we could use some of the legacy logic that we have, and basically do asynchronous processing in Erlang, from PHP. So what that gives you is some interesting mechanics that you can do. Like for instance, you can go and from one PHP script, you could be launching like N processing in parallel, without blocking. And that is something that PHP doesn't allow you because PHP doesn't have threading. So everything is serialized. So this was something like very, very beneficial for some of the stuff that we had to do, because it would give us a nice way of being able to scale higher on a web server. Because if your scripts are taking too long to execute, you will kill your web server at some point, because you won't process enough requests. So this is an example of kind of MyPeb, which is like basically inserting, using from PHP, it's a simple function inserting encoding in Atom, and so it's basically a list with a tuple on the right, and Atom and a string, and it's basically sending this to insert into an ETS. That's a very simple example that you'll find on the website over there, but it proves the point of like very, very simple as far as. And then you basically encapsulate this in a class, and you've got just it's a simple call that you can call from PHP to do an insert. And it's kind of nice. I mean, it's kind of, again, it's like if you don't do PHP, it's really a weak point, but I think it's good for people out there like actually doing PHP. The data storage, we use MySQL for the most part because it's extremely reliable. Percona is very, very reliable. There is MariaDB as well, but Percona, we've been using it for like 5 years. So it is something that They have a cluster solution, and it's what we do is that we basically use sharding. So we'll do a master slave topology, which means like we also automatically fail over if something goes wrong. So that gives you like a way to basically keep running and have your system not stopping. So we have like everything is so whether it's RAID 10 or RAID 6, we try and make sure like we don't lose. If we lose a drive, the system keeps running, and everything is SSDs. So we only do SSDs because that's really makes a big difference, and that's not expensive on a overall. So partitioning your table, large volumes. I mean everything. What you have to do is basically partition everything. So I wanted to keep the MySQL because, the SQL expressive power using in our application, because SQL is one of the best declarative language when it comes to fetching data and selecting data. So not using SQL very often makes you kind of rewrite SQL equivalent when you have no SQL, because people are trying to come up with ways to do joins or implement secondary indexes, and then so we have a mix. We use NoSQL and SQL. So, but this is something that we have some interesting stuff you can use. Like UnderSocket is an interesting plugin that gives you like a bypassed SQL layer, and you can do a large number of querying per second. So it goes up to like 750, 800 query per second, K per second, which is pretty huge. So this is how we do the data sharding. We have like sharding topology, and sharding topology doesn't mean that you don't you're not I would say redundant. I mean we are redundant because you have primary master, secondary master, and slave, but each of these shards could be a cluster itself. So basically you end up having a sharding, a topology with clusters, and so that means like your cluster, your shard can actually handle a large number of players and data. So I give some numbers, but it is very it's been very successful. This is definitely one piece of software that is highly reliable. I mean, we don't have any corruption. We never get a corruption. So as long as you know your subject, you can really scale that thing. Redis is the second NoSQL store we use. Redis is one of the most stable pieces of software I've seen so far. It never crashes. It's extremely reliable. If it crashes, it's likely a memory corruption. Redis is single-threaded, and it's been tested like crazy, profiled, all the. At this point, it's like we use it because it's just plain reliable, and so we shard, and we do a cluster implementation. Well, not cluster, we do a master-slave kind of like redundancy, which allows us to automatically fail over. So we have automatic failover everywhere. So if we lose connectivity to a node, we just like go and fail over to the slave. And so that's been, so yes, of course, if you look at on the grand scheme, what does that mean? Does that mean that you have strict consistency? Well, you do have strict consistency to a degree, but what's happening is that we have a model where we can, we basically try and repair, some of the state of our objects in the cache if we detect that something is likely out of state, out of sync. So we do a pretty high degree of sharding, so we can afford to also like reset a shard without necessarily like impacting the performance of the application. That's another thing I want to talk about is like if you can always double by minimum. I think doubling at the minimum is you should always be able to double your capacity. Based on and have your throughput, being able to handle that. Because if you don't, you're going to have trouble. Like if you lose like a set of machines, like we can lose, for instance, the whole cache right now. We could run like maybe for a few minutes, but if we lose like half of the cache, we can actually sustain. We can actually keep running, which is something that we want to have. This is a must for us because these kind of things might happen. So, I recommend Redis. The topology is very simple, the same as like enslave, masters, HA, automatic failover. So this is, we have logical sharding. So you have you have physical sharding, based on a mod, or you can have logical sharding, it depends. For the database systems, I would recommend logical sharding because that's the easiest way to move data across shards. Some numbers we have is basically 3 million. Yeah, so we've done some interesting benchmark. Like it was actually more than a year ago. We were able, on our chat server, we had like a room with 3.5 million people. So these people were actually bots, but actual sockets connected. And we are using Sung, if you're familiar with Sung, XMPP benchmarking tool in Erlang. So we are using it to basically emulate, and we were able to broadcast to 3.5 million endpoint under 200 milliseconds message in a room. And so that was, of course, to do that, we had to distribute the chat room processing and broadcast on a cluster. This is something that we like to do because, again, we have ways to make people, to control how people are speaking in a chat room. So you could actually handle, you could be dealing with a very large chat room and be able to, have at least people like reading what's in a chat room. If we need to distribute something, for instance, we can use a channel. And that's kind of, that's work for us. We do, on the database side, we can handle like more than 100K writes per second, which is actual write on a store. And that's not in memory, it's on a disk. We can do 250K reads per second, so that's much easier, obviously. And we can handle like real-time battles. Well, it's like hundreds of real-time battles is definitely the big thing is like, you have on your phone, you could be dealing with 400 people on your screen trying to fight together, and all of this is an interesting challenge for the real-time, for Erlang, for us, because we have to make sure we can process all of this and translation. So the alternatives, stuff we've been looking at is Cassandra, React, and Couchbase. Cassandra, I used it 18 months ago. Unfortunately, we broke it because we go through some severe benchmarking, but I think it's better now, so this is something we'll reconsider. React, we did some testing a while ago, but now I think it's something we're going to be also looking at. Couchbase is something we've been also kind of like testing, but so far we are looking at what's going to be using next. I mean, but we're okay with what we have right now. So MariaDB is definitely something interesting as a MySQL, another fork, different from Percona. They've added parallel replication in 10.0, so which is good because MySQL replication is single-threaded. So with parallel replication, we'll be able to handle more writes on your cluster, which means like you will be able to really maximize your hardware, especially with writes, and because that's right now you can do like per cluster you can do 3 to 4K writes per second without any lag, meaning that any consistency issue or data discrepancy. The rest is like Tungsten is a great product to basically replicate data across different data sources. This is something that is really interesting to use if you want to have a high degree of edge share in your app, and if you are dealing with different type of data storage. They're a great architecture. So yeah, I mean, summary is like, global scale volume. It's like really try and bench, identify potential roadblocks, connection points. This is like negative testing, benchmarking, innovation. I mean, that's what we've done. Most of our stuff have been, we've kind of like tried and apply like firm principles, non-techniques to, to build, other implementations and make sure we can scale, even higher. So, yeah, so that's, and our plan B, our plan B is actually something that I always talk about when we do something on a game or maintenance, is always have a plan B, because things will go wrong, and if you don't have a plan B, well, that's going to be, you're going to get a CEO calling you at 2 a.m. in the morning. So, so we try to be careful about it, because this game, the game we have basically, if you stop the game, it's like, and then you start having like 100K people like going back like under 5 minutes. That's annoying. So it's not annoying, but it causes you to stress out a bit, especially if you don't have all the hardware in place to handle like a huge spike on that level. So yeah, so Machine Zone, we are pretty much like deep into Erlang. We've it's at this point it's like we invested a lot and we are building the team we built a pretty good team, very senior team of engineers. So, and of course we are hiring. So that's something that you guys are interested in projects. You can always check us out. So I'm pretty much done now.
Right. So,
do you have any questions?
Right. So we don't seem to be having questions.
I guess it's happy hour.
Yeah. So let's give a hand to.
Thank you guys.